How do input parameters affect thermodynamic modeling results? Have you ever wondered how the numbers and values we plug into thermodynamic models can change the outcomes? Let's break it down in a way that makes sense. Input parameters are the specific numerical values or physical properties that define a thermodynamic model. These include temperature, pressure, composition, and constants related to the substances we are studying. These parameters are essential because they directly affect the accuracy of the results we get from the model. For instance, thermodynamic models calculate important properties like enthalpy, entropy, Gibbs free energy, density, heat capacity, and phase behavior. If the input parameters are off, the results can be misleading. One key concept to understand is the equations of state. These are mathematical relationships that describe the state of a system. Common equations of state include the Ping-Robinson equation and the Soave-Redlich-Kwong equation. The accuracy of the input parameters for these equations, such as critical temperature and critical pressure, is vital. Even a small mistake in these values can lead to large errors in the predicted properties. Let's take density as an example. Density is a crucial input parameter that influences the calculation of transport properties like viscosity and thermal conductivity. If there is an error in the density input, it can affect the entire model and lead to inaccurate results. Similarly, parameters that describe molecular interactions can impact phase equilibrium predictions, which are important in many applications. In some cases, models use parameter fitting or regression based on experimental data. This process helps refine the input parameters to better match what we observe in real life. This is particularly important for complex systems where standard parameters may not capture all the behaviors we see, like interactions in proteins or non-ideal mixtures. When it comes to practical applications, choosing and validating input parameters carefully is key. This ensures that the outputs from simulations are meaningful and useful for design, optimization, or risk assessment. For example, in computational fluid dynamics simulations, having accurate input parameters helps predict how gases will flow and transfer heat. In summary, the input parameters we choose have a significant impact on thermodynamic modeling results. They determine how precise the calculated properties are and how well the model represents real systems. Choosing accurate parameters leads to reliable predictions, while poor choices can undermine confidence in the results. Understanding how each input parameter affects the model is essential for effective thermodynamic modeling.